Hello, my name is Xaver Arbinger. I'm Field Application Engineer at Texas Instruments. Welcome to my session. My presentation will answer this question. Is GaN the key to smaller, lighter HEV EV designs? First, I would like to start with an agenda. At the beginning, I will highlight the role of power electronics in automotive electrification. After that, I will dig into the details of power switch technologies. Then I will explain the challenges of using GaN FETS for high frequency operation. Afterwards, I will present an onboard charger design, and finally I will summarize the results and will answer your questions. You can see here that the automotive electrification is happening now. More than 100 electrical vehicle models have been launched since 2019. The challenge here for automakers is the charging time, the driving range, and the affordability. You can see here we have on an e-car a traction inverter, a high voltage DC-DC converter, and an onboard charger. And this means that the power electronics innovation is the key for said components. And the design goal here is to increase the power with little to no increase in size and weight. But to make things smaller, it's important to be more efficient. This means less surface is necessary to extract the heat. Therefore, it's necessary to achieve higher efficiency and higher frequency operation at the same time. We see a big trend in onboard charger and high voltage DC-DC converter. It's necessary to increase the power density and to reduce the size and the weight. This means new topologies and design approaches are necessary. For example, very common is a totem pole PFC stage, and this allows you to achieve 2 times higher power density, or to increase the switching frequency for a DC-DC converter. This allows you to reduce the size and the weight of the magnetics significantly. Also, a lower BOM allows you to reduce the manufacturing costs. And to achieve a faster time to market, a scalable solution from, for example, 3.3 kilowatt up to 22 kilowatt and addressing both 400 volt battery systems and 800 volt battery systems help you to reduce that time. And reliability is a key factor in automotive market, and you have to ensure that you are adopting new technologies or design approaches where you are confident. This is a comparison of different power switch technologies. We are comparing here GaN versus SiC and versus silicon. The diagram on the left side shows a comparison of reliability, costs, the switching figure of merit, the reverse recovery charge, and the capability to handle high voltages. I would like to start with the reliability, but will dig into the details later in that presentation. But you can see that silicon, SiC, and GaN are in the same area. To compare the switching figure of merit, GaN shows the best performance. The figure on the right side shows a comparison of the lost energy every time this FET switches. The silicon energy loss is outside of the plot because it is too high. SiC is around 4 times better than silicon, and GaN around 3 times better than SiC. You can see also advantages in terms of reverse recovery charge, because there is no body diode in a GaN device compared to other technologies. This means highest efficiency can be achieved by using GaN. GaN is limited to around 600 or 650 volts, but using a multi-level topology, higher voltages can be addressed. An example here is to charge an 800 volt battery with GaN. Regarding the costs, silicon is already in use since decades. It is an amortized technology and there are no major opportunity to reduce costs here. The price for SiC will go down, but only a few vendors can provide the substrate for SiC. Therefore, we anticipate the price of SiC will not go down compared to silicon and GaN. The price for GaN will go down in the next couple of years. And why is this possible? Because GaN is built on a widely available silicon substrate, which is lower cost to manufacture compared to SiC. Because of this reason, GaN costs will come down soon as the yield and the CPV improves. So that soon we can anticipate GaN can overtake silicon, can deliver better performance. I would like to show in that slide the impact when you're designing a high frequency application with discrete FETs. GaN devices are very often packaged as a discrete device and driven with a separate driver. From high frequency perspective, the equivalent circuit diagram will look like this and shows a lot of parasitic inductance because of bond wires of each package and leads. The simulation of the right side shows the impact of a common source inductance up to 5 nanohenry in a hard switching application. This limits the IDS peak current and slows down the transition time. When you are switching at high slew rates, this can cause switching losses because of higher overlap losses and longer dead times, ringing and reliability issue. Shorter dead time is the key to increase the switching frequency and to increase the efficiency. For example, 100 nanoseconds dead time at turn on and turn off means you have lost 20% duty cycle at 1 MHz operating frequency. The gate loop inductance includes the gate inductance and the driver ground inductance. The gate inductance is the inductance between the driver and the gate. In that case, it is the bond wire of the driver, the bond wire of the GaN, and the trace of the PCB. Depending on the package, it could vary from a few nanohenry up to 10 nanohenries. With a larger gate loop inductance, the ringing becomes higher. This effect is simulated here with a 1 ohm pull down to turn off the low side GaN FET. This appears around 9.97 microseconds, whereas the gate loop inductance is varied from 2 nanohenry to 10 nanohenry. In the 10 nanohenry case, the low side gate source voltage rings 12 volt below the negative gate bias. And this negative 12 volt is a huge stress on the gate of the GaN, which increase reliability concerns. The gate loop inductance for LC circuit with FET GaN capacitance can cause ringing with the risk of overshoot and the gate voltage overstress. This becomes a big reliability concern, especially for some GaN devices where the maximum allowable gate voltage is quite low. Selecting the right topology is just a starting point. And in combination with the smart engineered product like the TI GaN device, allows you to gain all benefits of this topology. You can see that the driver is integrated with the GaN FET on the same lead frame and the GaN gate is directly bounded to the driver output. This can reduce the gate inductance to less than 1 nanohenry and the gate loop inductance less than 4 nanohenry. And we added other smart features in the driver, which I will talk about later. This compact SMD package allows low parasitic lead inductances and enables enhanced thermal management with topside cooling. We demonstrated an DVDS-DG capability higher than 100 volts per nanosecond. But if the slew rate must be adjusted because of EMI reason, this can be done very easily. I will describe this in the next slide. This slide shows an overview of the automotive qualified 650 volts rated GaN power stage with integrated driver and protection circuit. You can see on the right side of the picture the 30 milliohm GaN power FET. The driver for that FET is already integrated. An unregulated 12 volt voltage supply is sufficient. The power supply circuitry to turn on and off the gate FET is already integrated. There is an LDO implemented to power an external digital isolator with 5 volt. The current sensor is already integrated to protect the IC from overcurrent or short circuit. Because the sensor is integrated, short circuits can be detected very fast. The IC has additional protections like undervoltage and overtemperature integrated. You can analyze the fault signals and distinguish between different fault cases. The integrated driver sends the GaN die temperature and outputs the information through a modulated PWM signal to the temp pin. The pen signal starts with 3% of duty cycle at 25 degrees centigrade and reaches 80% of duty cycle at 150 degrees centigrade. An additional interesting feature is the ideal diode mode of the GaN device. The GaN power FET with driver is integrated in a 12 by 12 mm QFN package, topside cooled with wettable flank, which is required in the automotive market. Very low thermal resistance down to 2.3 degrees centigrade per watt can be achieved. You can see in that slide the architecture of an onboard charger. This contains two different parts, the PFC stage on the left side and the CLLC stage on the right side. The red FETs are the GaN power FETs. This totem pole PFC is a hard switching topology. As the picture and equation shows, the switching power loss is dependent on dVdt time TR2, the IDT time TR1 and the stored charge in the device. The iGaN's integrated driver achieves fastest dVdt, helping to reduce TR2 in the red region. And in the blue region, when the IDT happens, the QFN package low CSI helps to reduce TR1. The yellow region is the remaining output capacitance. Because GaN has no reverse recovery charge, which is quite low for GaN compared to other topologies with comparable RDS on. The key to higher frequency operation in soft switch topologies such as CLLC is the VDS voltage transition from high to low during the dead time. In order to ensure that zero voltage switching happens during the dead time, the designer has to choose a dead time which is long enough and magnetizing current that is high enough to discharge the COSS capacitance of the FET fully. But the long dead time prevents you to increase the switching frequency, while a high magnetizing current causes circulating power losses and eddy losses in the transformer. The low COSS of GaN allows the designer to choose a small enough dead time and low magnetizing current. This is the enabler for frequencies beyond 1 MHz. The case study on a 6.6 kilowatt onboard charger shows the reduction of the magnetics while increasing the switching frequency. Let's take a look into the PFC stage. Increasing the switching frequency from 65 kHz to 125 kHz in a totem pole PFC reduces the volume of the magnetics by 25%. The magnetic volumes in the CLLC topology can be decreased by 60% while increasing the switching frequency up to 800 kHz. A key parameter specific for the automotive market is the lifetime reliability of GaN. As we approach the end of 2020, Texas Instruments completed more than 40 million hours of device reliability testing, and more than 5 gigawatt-hour energy has been converted already in application testing. The fit rate over 10-year life is below 1. Very important is the self-protection in extreme conditions shown here. The GaN device has been designed to withstand 720 volt surge and lightning. In addition, a short circuit protection is integrated, which is faster than 100 nanoseconds, plus a thermal protection to 150 degrees centigrade. Here is the summary. Higher efficiency plus higher frequency is a must for higher power density in HEV EV powertrains. Texas Instruments GaN delivers all-around merit compared to silicon and silicon carbide. GaN has better performance because of better figure of merit and no reverse recovery losses. And the costs are lower because it's manufactured starting from widely available silicon substrates, and the supply is not constrained unlike substrates needed for SiC MOSFETs. An additional advantage of Texas Instruments GaN FETS is that the driver is already integrated, and together with additional features, this helps the engineer to simplify the design effort and to minimize the downstream design risk. This answers a question from the beginning of the presentation that GaN is the key to smaller and lighter HEV EV designs. You can find on ti.com the data sheets, a lot of references, design considerations, application notes, tips and tricks, and so on. This was my last slide. And thanks a lot for your attention.